Hi, everybody. How is everyone doing? So I have posted a few announcements and some clarification on some things regarding participation and other things. So I'm going to talk about that first, and then we're going to jump into analysis of variance, which is in chapter 13. And today we're going to this is going to be a pretty short lecture today. Thursday, we'll go over all the hypothesis testing with this new type of hypothesis test and test statistic. But today I want to talk about just the conceptual things behind it. It's important to know what Anova does, why it's used, how it's helpful, and why we use it compared to why we would use it compared to other test statistics. It's a little more involved than the t-test or the z. Okay, so moving on. Okay, so first of all, for this lecture, I would highly suggest that you access these PowerPoints. They are in the announcements, and yeah, either print them out or just have access to them on your screen as I go through. And then, of course, any paper for notes and any pertinent questions that you might have, write those down, and then tomorrow in the Zoom meeting, we can go over those. Okay, so just a few housekeeping updates. So these are posted on announcements, but I wanted to go over those in person as well. So for participation, all right. So I'm gonna post lectures twice per week on an announcement. All right, so I'll send you two different announcements, two different announcements. They'll each have a lecture in them, just like the one today. And then you'll need to reply and write participation in the window. So that's what you've done before. The difference is that even if you attended the Zoom meeting, you still need to do that. Okay, so everyone needs to reply to the announcement. Okay, so this announcement, for example, this is that has the lecture in it. You need to reply to that, and even if you have been in the Zoom meeting. Now I have access to the participants' names who were in the Zoom meeting, but I also would like all the replies in the same place. And then I can also, cross-check if I need to the participants who were in the Zoom meeting. So anyway, so that's what you'll need to do. If you were in the Zoom meetings last week, go ahead and just reply to those. You can do it retroactively. I don't believe that there's a limit to the time that you can reply. I just check and see the date and time. Otherwise, go ahead and do that, and I'll make sure you get those points. Okay, so the lectures. Okay, so lectures. Before, I just wanted to do the lectures, on Zoom. Zoom would be sort of like our virtual classroom. But instead, it's after last week, especially after Tuesday, I realized that it's easier to post the lectures first and have you watch those, and then have you write down questions that need things that need clarification that you want me to go over again, and we'll do that in the Zoom meeting. So it's much easier to manage, knowing that everyone has sort of that foundational knowledge, and then we can go over it again and do some examples, all those things. We can do that in our Zoom meeting. So the Zoom meetings are actually not going to be recorded now because they're just going to be kind of like workshop days and question days. So unless I cover content that was not originally in the PowerPoints, then I won't record it, right? So it would be very helpful to you to attend the Zoom meetings. Everyone will have access to the lectures now, but yeah. So what we're doing today and Thursday are, it's going to be new. It's definitely more in depth. There's a lot of concept behind it, a lot of theory behind it that we're going to talk about today. So yeah, so I mean, I can't say anything else except that really need to join the Zoom. Okay, so that said, analysis of variance. All right, so here we go. So in hypothesis testing, we're often interested in observing more than two groups. So usually it's not just like male and female. Okay, we're a little bit more interested in knowing 3 or 4 or 5 or more groups and comparing those. So we use Anova. The t-tests are limited. The independent t-tests and the 2 sample t-tests and the 1 sample t-test are limited, and that they can only be used to test for differences in one or between 2 groups. So right, the mean minus and the mu difference, and then the sample mean minus the sample mean of the other group, those differences. So that's what the t-tests are. But the Anova gives us a little more sophisticated approach and a deeper look into our data. Okay, so analysis of variance is a hypothesis testing procedure that is used to evaluate mean differences between 2 or more treatments, also called treatments populations, or treatment groups, populations. Those are, those 2 words are interchangeable. So Anova is still comparing means, looking for mean differences. It's just that it can look for more than just 2, the means of just 2 groups. So that's why it's going to be more helpful. It's more commonly used, and it will give us more confidence that that we're able to conclude what we conclude. So what is the difference between two-way tests and Anova? Well, researchers can compare 2 or more treatments, which allows for much flexibility in design and interpretation of results. So we'll have, so we can look at our data, okay, in sort of many different ways. We're going to look at error a little bit more deeper, yes, I kind of get like a more of a 3-dimensional look. If we looked at a model of it, we could see in it, we could see outside of it, we could see differences, all of that. So it's definitely more, like I said, more involved and more sophisticated. So we could use, actually, let me get this. So we could use t-test for 3 more samples. So, we could do, like, if we had 3 groups, 3 samples, we could compare group 1 and group 2. We could compare group 2 and group 3. We could compare group 1 and group 3. So we could do an independent t-test or a 2 sample t-test with 3 or 4 or 5 or 6, groups. All right. The problem is that every time you run a 2 sample t-test, you are running more risk of committing a type 1 error. So if you remember with the independent t-test, you're comparing 2 groups and set an alpha of 0.05. Well, we'd be setting an alpha of 0.05 for every combination of 2 groups for the t-test. So that's going to increase our chance of type 1 error in other words, saying that we have an effect when really we don't, saying that there are significant differences between the means when really there is not. Okay, so it's really like a false positive. So we're going to increase our chances of committing that error if we use a t-test for multiple samples. So that's why we're going to use Anova. So this is what I really can be sometimes difficult to start thinking about. You have to kind of let it sit in your head and roll around a little bit. But I think that, we're going to get the basic idea of it. But it's really important to know exactly what you're doing with analysis of variance, because you're doing something different. Okay, so we have two terms: between group variance and within group variance. So so our within group variance would be like, so we have, say we have these three, okay, we're comparing three populations or three treatment groups, and are within, you know what, let me start with between. So our between sample variance is the difference between this group and this group, or this group and this group, or all three. So we're looking at between group differences or between group variances. That's what we looked at when we're looking at the independent t-test. However, with the the analysis of variance, we're also looking at the within group variance. So the within group variance is all of the scores that make up that population. So is there variability? Okay, the more variability we have inside within each sample, the more error we have. So we have the within group variance, and we're going to compare that to between group variance, right? Between is boop, 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 between these, okay? The mean difference, and then the within group is literally in each group, within each group, the variance. So we've talked about variability before, and we know that the variability value, right, we use to measure variability is the standard deviation, and then variance is standard deviation squared. So variance is what we're talking about, this variability. So the same thing, variability and variance is the same thing as error. Okay, so we actually don't want a lot of within treatment or within population, within sample differences. So we talked about this back in when we looked at variability, measures of central tendency, measures of variability. And remember we talked about how we want our scores to fall as close to the mean as we can, because that means there's not as much error. If it's not as spread out, that means that people scored about the same, which is close to the mean, which means any sample that we're going to draw is going to be closer to the mean if we have not a lot of error. Okay, so we want our less error. Okay, so we want our groups, our populations, you know, the curve to be kind of tall and skinny, right, to group around that mean. Okay, so here's kind of the breakdown of total of the analysis of variance. So if we're going to put it in this kind of chart, so we have total variability. All right, so what that means is just like all of the data. So all of the data that we have are variable. So we just are calling that total variability. So there's two components to analysis of variance. So we're going to take all of the data, we're going to divide it into two parts. One is the between treatments variance, and the other one is within treatment variance. Okay, and again, treatment means population, groups, even you could say samples. Okay, so all the groups that we're using, there's between treatment variance and there's within treatment variance. We're going to use the variance to calculate mean differences. So we're going to use the variance to calculate mean differences. So what is between treatment variance? Well, this measures the differences due to treatment effects, okay, and chance. So let's talk about treatment effects. Treatment effects is significant mean differences. So if you remember when we talked about the independent sample T last week, or the two sample T, if there was significant differences between the two groups, then we would reject the null hypothesis, and the treatment, we'd say that the treatment had an effect, right? So we're looking at mean differences. If there are mean differences, that means the treatment had an effect. And we're also going to measure chance, which is the same thing as error, which is the same thing as within treatment variance. Okay, so chance means error. So if there are treatment effects, great, but to what extent are those effects or those mean differences due to something that was outside of our control, something that just happened, it just, you know, was some lurking variable that we didn't control for, and that is what we call chance. Okay, so then the other part of Anova is we're going to look at the within treatments variance, which is exactly what I talked about before. We're going to measure the differences due to chance again. So here we're measuring both between, which is what we've been doing this whole time. We've been looking at the differences between two means. That's what this is, okay? The differences would be the treatment effect or the treatment non-effect. And then how much of that is due to chance or due to error. Within treatment variance is essentially error, okay? Meaning that there is the probability that, you know, if we reject the null hypothesis and we still have a lot of error, then possibly we committed some type of type 1 error. But normally, if we have a big treatment effect, we're going to have a smaller amount of error, okay, and a smaller amount of chance of something happening by chance that we're not expecting. Okay, so this is the actual formula for the Anova. The final calculation looks like this. So the F is our test statistic, just like the T was our test statistic and our Z had been our test statistic. Now we have the F. The F ratio actually is what we call it. We'll call it F. This is variance between treatments divided by variance within treatments. So we really don't have any fancy numbers or symbols. It's literally just the variance between treatments, okay? And so variance, again, we use the variance to measure if there are differences between means, okay? Or between the means of each treatment group, okay? So that's where we get our between differences or between mean differences, and also the amount of variance between those differences, the amount of error that exists between those differences. And then we divide that by the variance within the treatment. So that's the error, okay? And that's like the same thing like standard deviation or standard error, estimated standard error, it's error. So if you maybe have noticed a pattern where you have the F, so the Z, the T, and the F, they all have treatment effects or between treatments or between mean differences in the numerator, and then they all have some sort of error, whether it be standard deviation or standard error, estimated standard error in the denominator. There's no difference with this particular test statistic. We have variance, which in this case is error. The error is called within treatment, okay? So the variance within each treatment. So we want to, when we do our calculations, which won't be until Thursday, we have the sample variance, this is not new, divided by the sum squared over the degrees of freedom. Well, that's gonna form the essence of calculating the T or the F ratio. And so when we calculate it, we actually will have 9 different calculations. You know, we're gonna be looking at different types of sum of squares values and different types of degrees of freedom values, and getting some the variance, and then being able to put that into the F ratio and calculate the final F. Okay, but like I said, we're going to do that on Thursday. So a little back to the conceptual stuff. So our F ratio actually looks like this. So our T statistic was a normal distribution. Our F ratio is a positive distribution. Okay, so we have a positive skew. Our F ratio is only one tail. It's not 2 tails, and you can actually just see that, right? See that by looking at the picture. And then our F value, we want it to be very large. So we are going to set a critical value like we've done before. You have a different table to use, and I can post that as well. And then we want a large F, right? So we'll have our alpha at 0.05. We'll make that that'll be the critical value. And then we'll look to see if our final F statistic falls into that critical region. So that's why we want a large F, okay? So when it's a large F, we have greater chance of the treatment effect, okay? So why though? Why is it skewed? And even more of a question. I think I mentioned this. I'm actually going to go back here. So what was the value that stood for the null hypothesis in a normal distribution, like a t-distribution? What was the null hypothesis? The null hypothesis mean was 0. Remember, so we wanted so post treatment, we didn't want our sample to be around 0. We wanted it to be in the tails. However, with our F ratio, our F ratio actually is has a null hypothesis is represented by 1 and not 0. That's why we have this skewed distribution, okay? So why do we have a skewed distribution? Why is 1 our null hypothesis? Okay, so just kind of, I just wrote this up here again, the F ratio, variance between treatments divided by variance within treatments, all right? That's our F ratio. And then that is the same as our treatment differences and our differences due to chance. So we have differences, which is what we were looking for when we calculated the T statistic, treatment differences. But we're also looking for differences due to chance, in other words, the error. So we're looking for both treatment differences or between subject differences and either error within subject differences, however you want to say it. We're accounting for all of this, and that's just in the numerator, okay? So in the denominator, we're accounting for chance, so error. Okay, so when we go to calculate our F ratio, okay, if we have no treatment differences, so we have 0, okay, meaning there are 0 differences between the means, but we're still going to have error. We're probably going to have quite a bit of error if there's no differences, right? So our within treatment or differences due to chance or error, we're going to have a value for that. The value is going to be the same for the within, okay? So it's going to be the amount of error is going to be the same for both, and you take the amount of error divided by the amount of error, and you're going to get 1. So when we have no treatment effect, okay, we don't have any of this, all right? All we have left is our error, and the error is going to take on the same value, so that's going to be 1. All error equals the null hypothesis. Okay, so when the treatment has an effect, when the treatment has an effect, the differences between treatments in the numerator are entirely due to chance or error. So in this case, the numerator and denominator of the F ratio are both measuring chance differences and should be roughly the same size. Okay. So then when the treatment effect is 0, we obtain an F ratio of 1, because say we have the same value for differences due to chance and differences due to chance in the denominator. It has to be the same value or very close to the same value. Okay, so here's an example of the data that you'll be, provided. So I want to look at this, use it as an example, and then point out what some of these values mean. So let's say that I am a researcher and I want to know if temperatures, like temperature conditions, have an effect on how well students do on tests. So I divide my students up into 3 rooms: a 50-degree room, a 70-degree room, and a 90-degree room. Okay, and so I give them a test. You know, maybe I'll teach them something, and then I'll give them a test, and then I'll record their scores. So in this case, you know, it looks like there's an N of 5. And so let me just, I wanna use this to demonstrate within and between real quick. So I wanna know if there's a difference between 1 and 2. I wanna know if there's a difference between 2 and 3. I wanna know if there's a difference between 1 and 3. So I wanna know if they're just overall differences between these groups or among these groups, okay? So that is the variance between groups, okay? In other words, I'm using the variance between these groups. I am looking at the between group differences, but I'm also looking at the within group differences, okay? So I not only am accounting for, is there a treatment effect, but I wanna look and see inside each treatment, how much error was there. Okay, how much error actually occurred within these data, and what does that have to do with my decision to reject or retain the null hypothesis? So let's say that my 5 students in this group, these are their scores. The mean down here is 1. Forget all of this right now. I'm going to go through that. The second group, the 70-degree group, here are the scores, and then the mean for the second group is 4. And then for the third group, 90 degrees, we have 1, 2, 2, 0, and 0. So we have a mean of 1. All right, so my question is, are there differences between these means, 1, 4, and 4? Well, looks like there's some difference, right? So what this is only the within treatment difference. There's no comparing means, okay? We're just looking at the differences. So we could say, are there differences in group 1? Were there differences in that room? Okay, it looks like there was, okay, but not a lot of difference, okay? But the mean was overall 1, so they scored pretty low on average. Number 2, what was the variance in room 2? Well, it looks like they actually had a mean, of 4. So so this group scored, average of 4. This group, okay, scored an average of 1. All right. So instead, though, of looking at differences here, we're looking at the variance between just these groups, okay? That is the within group differences, And then we can find the error, okay? This is where that error lies, okay? And see how that relates to the treatment differences or treatment non-differences. Okay, so a few things to know. In Anova, the independent factor is known as the independent variable is known as the factor, which in this case is the temperature conditions. All right. The factor can have 2 or more treatment groups, as we know, also known as levels of the factor. In this example, there are 3 levels of the factor temperature. Okay, so 1, 2, 3. The number of levels is indicated by 3, so by K, thus K equals 3. Okay, and so I have K equals 3 right here. You might need to calculate this on your own, but all K is just how many levels of the factor there are. In other words, how many groups are in this study. Okay, so again, this chart, I want to point out a few things about these numbers and letters here, what they mean. So the total number of scores in the entire study is indicated by N. Okay, so when all the samples are the same size, N equals K times the actual N, okay, of each group. Group this small, you can just count up, okay, the number of people in the group, or you can take, we have 3 groups times 5, okay, and you get 3. Okay, so that's our K. The total for each treatment condition is identified as T, so that's these right here. So T, okay, means the total. So it's when you add this up, 0 plus 1 plus 3 plus 1 plus 0 is 5. 4 plus 3 plus 6 plus 3 plus 4 is 20. 1 plus 2 plus 2 plus 0 plus 0 is 5. Okay, so that's the total. How else could you calculate it? I'm sorry, how else can you use the symbols? Well, the total for a specific treatment can be identified if you want to by adding the subscript to each. Okay, so maybe that'll be easier when you're using the data later on, that you can differentiate between the group totals. Okay. And looking at this data one more again, so each score, this is the sum of the squared scores. So we would square all the scores first, and then we'd add them up, which means summation, right? And if we squared each of these scores and then added them all up, it's like the sum of squares, right? So we get 106. So the sum of all the G is the sum of all scores, okay? So this is when we add just the raw scores up. It should equal 30 in this case. That's the grand total. You can also just add 5 plus 20 plus 5, right? And we'll get 30 in this case, okay? And so that is, let's see. So the hypothesis testing we will do on Thursday. Be on the lookout for the lecture. That one's going to be a little longer, so I'm going to post it as soon as I can. But we're just going to be doing the same thing, guys. State hypothesis, get the alpha, which will be 0.05 again, look at the critical region. We're going to have to use a different table. Compute the F ratio. We're going to analyze all the components, which will be 9 separate calculations until we get our F ratio. We're going to plant our F ratio in the distribution to see if it's in the critical region, and then we're going to make our decision. Okay, and we're also going to test for R squared as well, the effect size. Okay, all right. So that's it for today. I have posted some questions that you can attempt on your own. It's just based on the concepts that I just went over, and we can talk about it tomorrow. You can wait till tomorrow to go through those, and we'll talk about it in class. And if you have any questions, and I hope you do, because this is kind of abstract type of stuff. So if you do, please ask tomorrow. I hope to see all of you tomorrow on Zoom. So you can go ahead and reply, all of you can reply and write participation to the announcement that this is in. Okay, so anyway, let me know if you have questions. Otherwise, I will see you tomorrow. Stay safe and have a good rest of your day.